So today we're going to start chapter 4. Basically chapter 4, we will be learning about probabilities, which we use inferential statistics. So the rare event rule is the first thing that we're going to kind of understand. It says if under a given assumption, the probability of a particular observed event is extremely small, we conclude that the assumption is most likely incorrect. So basically saying if something has a very small percentage of actually happening, then we say that our original assumption was probably a bad idea, was incorrect, okay? So to start this, by the way, this section is for many students. This is one of the harder sections. So please, ask me for help when we have our meetings, or email me and set up a time or something. But normally this is a difficult time for a lot of students. So probability definitions. An event is any collection of results or outcomes of a procedure. A simple event is an outcome or event that cannot be further broken down into simpler components. The collection of all possible outcomes is called the sample space, oftentimes denoted as S. Okay, so this first example says, consider the following. So a woman has a single birth, example of a gender event, and the sample space. So we know that, we're going to have, it's either going to be male or female. And that will be our, barring any differences, that'll be our sample space. So we'll call that S. The example could be that it's female. So we could say that F for female would be the event, right? So now if a woman has 3 births, this changes things. So what if a woman had 3 births? An example could have been, well, it was a female, female, male. That could have happened. So she could have had, a girl, and then a boy, or a female, female, and male. Now this sample space will be much bigger. Let me write this a little smaller because I'm going to run out of room. Okay, so now this sample space is going to be much larger. What am I drawing here? Okay, so this could be male, male, male. Could be male, male, female. Could be male, female, male. Male, female, female. Female, male, male. Female, male, female. And female, female, male, and then female, female, female. So that's what could happen in this situation. If she had 3 births, it could be any of these 3. So that's called the entire sample space because that's everything that it could have been. The result of 1 female is a simple event because it cannot be broken down further, but the event of 2 females and a male is not a simple event because it can be broken down into simpler events such as female, female, male, female, male, female, or male, female, female. So basically when there's alternate ways for the same thing to happen, that would be not considered a simple event. Okay, so a lot of times what we're going to use is we're going to use probability, and you'll oftentimes see it like this: probability of event A, or you might see probability of event A or B, or I might even write it like probability of A union B. This and this mean the same thing. So this notation, or this word or right here, means the same as this union symbol. There is no difference between the two in this class or in most math classes. Okay, and it says in this class, when probabilities are expressed as decimals, use 3 significant digits, 0.241 or 0.00056. Both have 3 significant digits. I'm not going to go too crazy on significant digits. A lot of times what I'll say is, in the homework or whatever, it'll say round to 3 decimal places. A lot of times for probability, we normally use 3 decimal places unless it's specified otherwise. But significant digits is not something I'm going to go too crazy on. But with the leading zeros, these zeros don't actually, aren't considered significant. These 3 are. And it depends on, I've also seen it talked about in different ways depending on what you're dealing with. But again, a lot of times for probability, we're going to use 3 digits of accuracy in terms of decimal places, unless specified otherwise. So it says relative, oops, oh geez. So we have probability approaches. So the first one is relative frequency approximation. The next one will be classical approach to probability. And the third one will be subjective approach to probability. Okay, so let's look at this first one. A procedure and conduct a procedure and count the number of times that A actually occurs. And remember, this is how we're going to say probability of event A occurring. It doesn't mean P times A. It means the probability of event A occurring. So we would say the probability of A is likely to occur the number of times that it actually happened, or I shouldn't say likely to occur. The probability of A occurring is the number of times it occurred divided by the number of trials, okay? So if we were flipping a coin, 10 times and 4 times it was heads, that's the number of times heads occurred. So that was 4 and the number of trials was 10. So that would be 4 out of 10 or 40% or 0.4, okay? When trying to determine, for this example, when trying to determine probability of A, where A's attack will land point up, we must repeat the procedure of tossing the tack many times and find the ratio of number of times the tack lands point up and then to the total number of tosses of the tack. Because if you think about it, you can't guarantee, it's not like flipping a coin where there's a 50-50 chance. We don't know the probabilities off the top of our head of flipping a tack. Like, does it have like a built-in probability? So what you would have to do is flip it hundreds, thousands, 10,000 times to try to determine how that tack operates in terms of probability and landing on its side or landing on the point up, okay? So a classical approach to probability requires equally likely outcomes. So each outcome has to have an equally likely chance of occurring. This is the word chance of occurring. The probability of event A is the ratio of the number of ways A can occur to the total number of outcomes in the sample space. So number of favorable outcomes to A, number of outcomes in the sample space. Okay, so this is kind of a classical approach. We use this one sometimes too. So it says, when trying to determine the probability of A, where A is a die will land 2 on a 2 with a balanced fair die, each of the 6 faces has an equally likely chance of occurring. So this one has probability of by landing on an even number. So this is something that you guys have to start, adapting. You could, like, if I asked you, what's the probability of a car going over 60 miles an hour? You could say probability of a car going over 60 miles per hour. Like, you can write that out. Now, in general, we like to try to shorten that up. So we might say probability of a car, right? So I might just say probability of C. A lot of times I try to use abbreviations or something so I don't have to write out those long stories. And a lot of times we let variables like A, B, and C represent certain events. So this could just as easily have been written probability of A, where it's understood that A is landing on an even number for this particular problem. So this would be, well, how many even numbers are there? There's, on a 6-sided dice, there's 2, 4, and 6. So there are 3 even-sided die. And then it says divided by the number of outcomes in the sample space. Well, when you roll a dice, you could get a 1, 2, 3, 4, 5, or 6. So there are 6. So the probability of getting an even number is 1/2. Okay, sometimes you can leave it as fractions depending on how they want it, or sometimes you give them the decimal. And again, it just depends from question to question. A lot of times I like fractions better, but fractions must be in simplified form, right? Divide this by 3, we get 1. Divide this by 3, we get 2. Okay. So the subjective approach to probability, the probability P of A, the probability of event A is estimated by using knowledge of relevant circumstances. When trying to estimate probability of rain tomorrow, meteorologists use their expert knowledge of weather conditions to develop an estimate of probability. So we could use something like this: gender of children. If a couple had 3 children, what is the sample space for the gender of the 3 children? Oh, but really quick, a follow-up. This problem almost seems like this one is not, this problem in the notes seems like, oh, so yeah, this doesn't mean, so this is kind of, they should have like a bar here. That's where that stops. This example 1 is not necessarily related to rule 3. So think about this, like, when they're trying to predict the weather, they base it on certain information they have and circumstances. So like, what if they took the weather over a 20-year period in this certain valley for this month for 20 years straight? They would use that data to try to talk about the outcomes. So that's what they're talking about estimated by using knowledge of relevant circumstances, okay? Okay, so now they're gonna give us 3 examples, and we're gonna try to see which one. So this says, if a couple had 3 children, what is the sample space for gender of 3 children? Well, we already did this problem up here, right? I already did this, so I already know that the sample space, you know, is from above. I'm not going to write it out again, but you guys can. We know it'll be male, 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 right? Male, male, female. And I'm just going to do dot, dot, dot because we just did it above. And then we'll end up at female, female, female. Okay. So let me see here. Oh, I'm missing a page of my notes. Hold on 1 second. There we go. Okay, so then it says, assuming having a boy and having a girl are equally likely, what approach would we use to calculate part C? So part C says, what is the probability that 2 out of the 3 children are boys? Since we know the entire sample space, I have a feeling that this is going to be rule 2, classical approach to probability, number of favorable outcomes. And don't think of favorable as like positive. Favorable just means whatever you're looking for that particular problem. So in one problem, you might talk about how many girls that would be favorable. And then in another problem, you might say how many boys that would be favorable. So we come over here and we're going to use rule 2, right? And this is what is the probability that 2 out of the 3 children are boys? So what we do is we come up here and we're going to look at our sample space. How many of these in the sample space had 2 of them out of the 3 children are boys? So let's see here. Here's 2 boys, here's 2 boys, here's 2 boys, and that's it. All the other ones either have 3 boys, 1 boy, or no boys. So there were 3 of them. So we're going to come back over here and we're going to say probability of 2 out of 3 children. Are boys. Okay, and that would be 3 out of a sample space of 8. If we count it up here, there would be 8. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possibilities, okay? And 3 of them have 2 out of the 3 children are boys. Sometimes you can also, if you want to think about how to build a sample space, you think of how many possibilities are there each event. So the first event, boy or girl, there were 2 possibilities. So we're going to do 2 possibilities, and then how many times was that event going to occur? There was going to be 3 children, so it's 2 to the 3rd. So this is 8. This tells us the size of the sample space. So as you could see, sample spaces could get really large. What if they were talking about 7 bursts? Then it would be 2 to the 7th, and then we would have 2 times 2 times 2 times 2. I think that's like 60. I think it's like 128 or something like that. So as you could see, it could get out of hand. We wouldn't normally want to write out that many elements in the sample space. So a lot of times what we do is we just like to know the size of the sample space so we can divide by it. Okay, so example 2, find the probability that NBA player Reggie Miller makes a free throw after being fouled. At one point in his career, he made 5,915 of 6,679 attempts. What approach are we using for this particular one? So let's see here. Rule 1 says relative frequency of approximation. So number of times event A occurred divided by the number of trials. And then this would estimate as follows. So we're going to try to base on previous information. We're going to use rule 1, I guess. Yeah, let's use rule 1. So rule 1 is going to be the probability of A, and it's the probability that he's going to make a free throw. So they do this all the time in basketball games. They'll flash the stats as a guy's making a free throw. They'll say, oh, he's an 85% free throw shooter, meaning that over the past year or his career, he's made 85% of his free throws. So they're trying to use that to tell you what's the chances he's going to make this free throw. So for Reggie Miller, it was 5,915 divided by his total number of free throws, which was 6,679 at one point. So this is going to be 0.8856, but I said that we should use 3 decimals, so I'm going to use 0.886. So he has a probability of about 0.886 of making a free throw after being fouled. So probably not somebody you want to foul because he almost has a 90% chance of making the shot. And most basketball players are below 50% when they normally shoot. So if they're just shooting a regular shot, they're below 50%. Some are, 30 and 40%. But if you foul them, they become almost a 90% shooter when they go to the free throw line. So it's definitely not something you want to do for somebody like this. So that's just how they can use statistics in a sports atmosphere. Okay, what is the probability that your car will get struck by a crashing meteorite? What approach are we using? This would be rule 3. And again, we don't really have any background knowledge, so we need info. They didn't give us any info on meteorites. We'd be relying on some data on meteorites hitting cars or whatever like that, which I'm assuming is almost near impossible, very, very unlikely. Okay. So now let's talk about the law of large numbers. Okay, so law of large numbers says for any event A, hold on. Oh, right up here, sorry. So law of large numbers, LLN, as a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. So here they show flipping a coin, 1 to 100, and how many were heads and how many were tails. And again, so that's not saying that you can't flip heads 5 times in a row. That can happen. And so then you can't then go make an assumption that, oh, this coin only flips heads. It's 100% because I did it 5 times in a row and I got heads. That's not how it works. What the law of large numbers is saying is that it's almost like the true probability or the relative frequency probability of an event tends to approach the actual probability. So if you flip a coin 5 times or 10 times and you get 8 out of 10, let's say 8 out of 10 of them are heads, that doesn't mean that that coin is now forever going to be 80%. That just means that you need to do more trials and more flips of the coin. As you start approaching 1,000, 10,000, 100,000, the true probability of the coin will show itself. So it'll eventually start approaching 50% heads, 50% tails. So if you flip it 1,000 times, more than likely you're going to have around 500 heads and around 500 tails. Within reason, maybe like 507 or something like that of heads and 493 of tails. But that's what the law of large numbers says, is the true probability will eventually show itself from the relative frequency probability with enough trials. That's what the law of large numbers tells us. Okay. So probability law for an event A, for any event A, the probability of A is between 0 and 1 inclusive. So no event can be more than 100% or more than 1 probability, and no event can have a negative probability or less than 0, but it can have a 0% chance. In this class, a lot of things are like very small chances of happening, but we don't normally call them 0 unless we're rounding off. All probabilities are values between 0 and 1. Or 0 and 1 as well. A probability of 0 means the event is impossible, whereas a probability of 1 means the event is certain to occur. And basically think of 1 as 100% likely and 0 as 0% likely. Complementary events. So the complement of an event A, denoted as A complement or A bar. I oftentimes will use A bar, consists of all the outcomes in which an event A does not occur or does not occur. So the complement rule, probability of A plus the probability of A complement has to equal 1. So this is something that we can use in order to find probabilities by subtracting, okay? So here it says, if 202 out of 1,010 randomly selected American adults are smokers, find the following probabilities. So what's the probability of being a smoker? So probability of being a smoker, okay? So that would be 202 out of 1,010. Okay, so we get this isn't approximately, this is exactly 0.2, okay, of not being a smoker. So we could just do, okay, how many people aren't smokers? Well, if 202 are smokers in this sample, well, then that must mean 808 are not. So probability of not smoker, okay, that would be 808 out of 1,010. So that would be 0.8, okay, or 4 out of 5. Now, when they say probability of not being a smoker method 2, what they want us to do then is they want us to find the probability of not being a smoker by doing 1 minus the probability of being a smoker, okay? So we know that being a smoker has a probability of 0.2. So what I'm going to do is I'm going to say 1 minus 0.2, which is equal to 0.8. So in this method, I can use the complement, right? So this is the complement to this, and they have to add up to 1. So you have not smokers and you have smokers, and the total probability has to be 1. You're either a smoker or you aren't, okay? So what they're saying is, since the total probability has to be 1, we just do 1 minus the probability of A, and in this case, this was the probability of being a smoker. So I did 1 minus the probability of being a smoker, which gives me 0.8. But that's the same I did over here. So both ways work, but a lot of times this 1 minus works for problems that would be much more difficult, where it is kind of hard to find this way, okay? Right now it was easy, so you don't mind. You're like, oh, it worked either way. But eventually some of the problems, finding the complement is much harder. And what would be easier is just to do 1 minus the alternate and the complement, and you would be able to find the answer. And I don't really do odds in this book. I think one might have slipped into the homework. I might have to take it out. But in general, yeah, we don't do the odds. I do a little bit of, ooh, this problem got kind of messed up on the sheet. So hopefully you guys can see this okay. Okay, so let's go to 4.3. Remember, 4.3 is probably 4.2 in your book. This is an older edition, so it's a little off. So this is something very, very important, and 4.4 will also be very important. So it says the addition rule. So this applies to finding OR probabilities. So this is a really big deal for us. So it says the probability of event A or event B occurring is equal to the probability in a single trial event A or event B occurs or they both occur, okay? So whenever you see, and this is the Venn diagram, so it says the probability of A. So this is the probability of A, this is the probability of B, and then this centerpiece is the probability of A and B. That's how you can write this same thing right here. So they're saying that that centerpiece is if A and B both occurred, okay? But again, we're dealing with the OR, and in the OR, the and comes up. So that's something we'll have to discuss. So the probability of A or B is equivalent to saying the probability of event A occurring plus the probability of event B occurring minus any overlap between probability and of A and B, where the event A and event B both occurred, okay? So you have to subtract that, because if you notice, if I were to shade this in, right? If I were to shade that in, and let's say I called that A, right? And then let's say I were to shade this in, right? And let's call that event B, right? Now the problem is that event A and event B both shaded the center location. So I've shaded it twice. So what we do is we subtract off right here. You see the subtraction? We subtract off one of the shadings, okay? So we don't end up shading it twice. So that's what the probability of A and B with that subtraction accounts for, is the fact that you counted this little center section. You technically count it twice, and so you have to subtract off one of them, so you only count it once. Okay, so let's look at this. This is a really common test type question. Oh, right here it says subtracting A and B avoids double counting. So that's literally what we're doing. So it says pre-employment drug screening. So below in the table are the counts for drug use and drug screening test results of 300 subjects applying for a job. So we have a positive test, 119, and they actually did use drugs. We have a positive test of 24, and they actually did not use drugs. So the test incorrectly said that they did use drugs. We have a negative test of 3 for people that actually did use. So the test missed it, they got away with it. And then we have 154 negative tests for people that did not use. So that's confirming that they didn't use drugs. So it says, find the probability of selecting a subject who had a positive test result. So let's see, probability, and I'm just gonna put a plus sign for a positive test result. So how many people had a positive test result? Well, 119 had a positive test result, but were using drugs. And then 24 had a positive test result, but we're not using drugs. So all I'm gonna do is I'm gonna do 119 plus 24, okay? And then how many people total were there? 300. So this is going to be what, 143 divided by 300. So whatever that is on my calculator, that gives me 0.47666. Okay, so 0.47666. Oh, it's 6 bar. So I'm going to round this off to 0.477. Okay. So we have 0.477. So we have a probability of 0.477 of subjects who are going to test positive. And then the next problem says, find the probability of selecting a subject who used drugs. So probability of used. Okay. So let's see, how many people actually used? Well, we have, once again, let's look. We have 119 and 3. So that's going to be 122 over 300 people. So I get, if I use my calculator and I round off, I get 0.407. Yep, 0.407. Okay, so that's our probability for this one. That's our probability for this one. Now it says, find the probability of selecting a subject who had a positive test result or used drugs. So probability of positive test result or used drugs. So that means we have to do the probability of a positive plus the probability of used minus the probability of plus and used. Okay, so let's see what we got here. So probability of plus, we know that that is 0.477, right? I'm just getting that from right there. We know the probability of used is 0.407. But now we have to subtract off the probability of plus a positive test result and used. So the best way to do that with a table is literally all you do is you just draw a line for positive. So all the positive test results go this way. And then you draw a line under used. So all the used go this way. So where did I cross? So I crossed right here. That was at 119. So I'm going to come over here and I'm going to say minus 119 over 300. You know what I'm going to do? Instead of using the decimals, I'm going to use the fractions just because this guy is still in fraction form. So this is 143 over 300 plus 122 over 300 minus 119 over 300. So we do 143, was that plus 3? So we have 146 divided by 300. And I get 0.487 if we round off to 3 decimals. And that would be the probability of having a test result, positive test result, or using drugs, okay, for this particular study. So again, all I did was I took and I said, okay, positive test result, and then use drugs. Where did the lines cross? Right there at the intersection. That's why an and statement is often called an intersection. So it's the intersection of 2 sets, okay? All right, so the addition rule is really nice for disjoint. So if events A and B are disjoint or mutually exclusive, if events A and B are disjoint, oh, that's bad English, I gotta fix that. So it says, if the 2 events cannot occur at the same time, disjoint events do not overlap. So basically what it's saying, okay, if you wanna say that 2 events are disjoint, that means that they have to be mutually exclusive, meaning that there can be no overlap between them. So notice here, here's event A's probability, here's event B's probability, but they don't have any A or B, or I'm sorry, A and B. They don't have any overlap. So no overlap, right? So because of that, You know how up here in this formula we had to subtract off because we had overlap and counted twice? These are super nice. There is no overlap. So if you have two disjoint sets, you don't have to worry about subtracting it off, because if you're trying to subtract off the intersection of two sets that don't cross paths, you're going to be subtracting off 0, right? So that's why it doesn't matter. So technically you could write it like this: probability of A or B is equal to the probability of A plus the probability, of B minus 0, because there is no overlap. So that's just the probability of A plus the probability of B, right? So that's all they're saying, that if there's no overlap, then why do you have to subtract off? So here's an example. It says political affiliation. So it is estimated that 23% of Americans are registered Republicans and 32% are registered Democrats. If an American who is registered to vote is selected at random, what is the probability that he or she is a Republican or a Democrat? So now this is assuming, once again, we don't care if you're a Democrat and you vote Republican, and we don't care if you're a Republican but you vote Democrat. This is saying, what are you registered as? So you can't be registered as a Democrat and a Republican at the same time. You can't do it. So these two events are exclusive. So it says, what is the probability that he or she is a Republican or a Democrat? So I'm going to do probability of Republican or Democrat. Notice we're going to randomly grab somebody, and we have to write this as probability of Republican plus probability of Democrat, and then we have to subtract off the overlap. But you can't be a Republican and a Democrat at the same time, so it's minus 0, so I'm not even going to write it. So then the probability of a Republican is 0.23, and the probability of a Democrat is 0.32, so this should be 0.55. Let me double check. Yep, that's it. So that should be all there is to it. So I think that's going to do it for this first video. I'll start another video for the end of chapter 4. It might take 3 videos, but this will be the end of the first one. Okay, you guys, thanks for watching, and see you in class.